Okay, so let's just start with announcements. So exercise set 3 due today. There's gonna keep being exercise sets, and they'll still keep having a decent chunk of questions on them, but I'm gonna start making almost all of the questions optional. So, because I want people to be focusing on projects instead. So for example, on number 4, I think the number of non-optional problems is a total of either like 2 or 3 problems. Okay, so that's really gonna be tailing off now. Speaking of the projects, so I did finally post an initial batch. You should have an email with that link. It's not linked to from the course page. So if you didn't get an email from me, tell me, okay? And you can go to the list of the projects. I posted 10 from this first part of the class, the first 3 weeks. I posted close to 10 more for this week and next week, and I'll post a few more for the last 3 parts soon as well. There's no hurry. It's not first come, first serve or something like that. So what I want is from everybody a week from Friday, which is February 7th, I would like your top 2 choices, and then I'll make some kind of centralized matching of who gets which project. And again, one of the things that's, this is, the smallest class I've taught in a while, and so I'm really looking forward to the opportunity to actually, talk to students individually. So feel free to, involve me in the process if you want questions about, you're wondering whether paper A is too difficult or paper B is too boring. Definitely feel free to ping me by email for some advice. Okay. Final announcement by sort of semi-popular demand, I'm going to say. There's going to be a bonus lecture, maybe there'll be 2 probably over the quarter. So the first one, which will be more about the theory of gross substitutes valuations, that's going to be a week from Friday, so February 7th, 12:15 to 2:05. It will not be videotaped, so really come if you want to see it, and it's going to be in Gates 359. Okay. So any questions before we get started?
February the 1st or 7th? Sorry.
7th, yeah, Friday, sorry. Yeah. So that was the time slot that most people could make. So, okay. So where did we leave off last lecture? So so the first part of this class was about tractable special cases where you could maximize welfare in polynomial time, implement the VCG mechanism in polynomial time, and ideally even get ascending implementations in all of those cases, in some sense a strictly more difficult goal. So let me just close the loop on that. I didn't actually talk about ascending implementations for gross substitutes valuation, so I just want to have a few comments about that before we move on to less tractable cases. So recall gross substitutes, that was what last week was all about. That's this condition where if you're a bidder and you lose some of the items, but the items that you're still retaining still have the old prices, you don't want to relinquish them. Okay, so in an ascending auction, you still want what you've got at any point in time, even as prices have gone up on the other objects. And we proved a bunch of stuff about that last week. The second lecture last week was about welfare maximization, and we worked pretty hard to prove that you could actually do it in polynomial time. And that took some work, took some assumptions. We needed to assume you could use demand queries so that we interact with these black box valuations. You give them a price vector, they tell you back the preferred bundle. And we use the ellipsoid algorithm, which is this sort of heavy machinery linear programming algorithm, which says, oh, as long as there's a polynomial time separation oracle, you can solve the linear program in polynomial time. So those, there are some bells and whistles on those results. You can get away with just value queries. There are some complicated combinatorial algorithms that don't use the ellipsoid method. But anyways, the main point is polytime with gross substitutes valuations. So at least we can get a D6 solution, VCG. So what about the more ambitious goal of getting an ascending implementation? So this is actually a tricky question. So first of all, let's remember what that means, or a necessary condition, as we've discussed, by a combination of the revelation principle and uniqueness of prices. At minimum, for an ascending auction to be ex post incentive compatible, it better be the case that if bidders bid sincerely, the end result is the VCG outcome, both the allocation and the payments. Okay, so we've mentioned this a few times. If all we wanted was the VCG allocation, meaning a welfare maximizing allocation, we know how to do it. The Kelso Crawford auction converged to a Wazian equilibrium. In particular, it's an efficient allocation. So the hard part is the prices. And in fact, you actually can't do it. Okay, so one of the results in this Gould-Sticchetti paper say that actually there does not exist ascending auction for GS that always terminates at the VCG outcome. Okay? And it's really quite a nice example. On the optional exercises, I'll just sort of sketch how the example goes. It's just it's 3 bidders and 4 items. And the thing I want to emphasize is this is not a computational impossibility result. It doesn't say there's no polynomial time algorithm or something like that. It says it's information theoretic. So it says if you restrict attention to just having an increasing price trajectory and interacting with bidders only through demand queries, you simply cannot learn enough about what they want to be guaranteed to compute the VCG payments when you terminate. Okay, so it's purely information theoretic. You just don't get enough info if you restrict prices to be ascending. So this is a sense in which, while gross substitutes are sort of the limit of tractability, this was a sense in which it's actually strictly harder than the first 4 scenarios that we studied. So that's good to know, interesting to know. Now there have been a couple proposals in sort of the ascending auction sort of flavor to, expand what we allow as an ascending auction and therefore elude this impossibility result. So the first thing is a paper by Azabel, the same Azabel from the clinching auction for scenario 4 for multi-unit auctions. And Azabel proposed allowing more than one ascending price trajectory. So in some sense, the prices go up and you ask a bunch of demand queries, learn some stuff, and then you kind of restart somewhere and do it again, and you do that a bunch of times. And he showed that if you're allowed to sort of have n+1 ascending price trajectories, then you can get enough information to compute all the VCG payments at the end of the day. And you do get a ex post incentive compatible welfare maximizing mechanism for gross substitutes. So can compute the VCG outcome using n+1, here n is the number of bidders, ascending price trajectories. And in some sense, this is in the same spirit of how to implement the VCG mechanism you solve n+1 welfare allocation problems. So in the same thing here, you're going to have one price trajectory where in effect, you're asking demand queries from all n of the bidders, and then you're going to have n different other trajectories where one of the n bidders is excluded. And at the end of the day, you stitch all that information together to compute the VCG payments. Okay. So this algorithm is quite interesting, sort of as a proof of concept. It really says, you can take these just simple ascending auctions like Kelso Crawford, which only get you a Walrasian equilibrium and don't get you VCG payments, and somehow build on them in a clever way and actually get enough information to get the VCG outcome. And you only use item prices the entire time, so that's interesting. But it is pretty complicated, so I'm not going to talk about it more in class. It is one of the projects, if you're interested, to read about this auction. And because of all these ascending price trajectories, I don't really know of real-world auctions that resemble this particularly. Okay, so it's a cool theoretical construct, but I'm not sure it's more than that. It can also be thought of as an extension of the clinching auction for identical items that we talked about for scenario 4. The tricky thing here when you have multiple goods is as the prices go up, the demand for a good need not only go down. So if it's identical goods, if everything's the same, the higher the price, the lower the demand. If you have a bunch of different goods and you fixate on just one item, it may be that the demand shifts from going up and down because prices on all the different goods are sort of simultaneously going up. So you have to extend the clinching auction to deal with not just clinching, but also unclinching, in some sense, refunding bidders as you take items back away from them. So that's sort of the high-level gist of how this works. Okay, and that's all I'm going to say in class. So the second way that people have expanded what's allowed as far as ascending auctions and dodged the Gould-Stiketty impossibility result, and is more sort of closely connected to what people do in practice, is to allow bundle or package bidding. So some early suggestions of how this might be done were Parks and Unger and Azabel and Milgram. And again, the latter paper here is one of the project topics, if you're interested. And so this is sort of related enough to things we've already said that I'll give you a few more details right now. So the idea is, our auctions are going to be more powerful than before. Rather than just maintaining a price for each item, the way we've been doing all along, for every possible subset S of goods, and even for every possible bidder I, we're going to keep track of a different candidate price. Okay, so bundle prices, PIS, for all bidders I, and for all bundles of goods S. So let me show you how this, one way this could work. There's many ways you can do these auctions, but let me just give you a very simple one. And this is going to be very similar to the Crawford Knower auction. So that was that one with unit demand bidders, where we just had people continually bidding on their favorite good, okay, over and over again. So we're going to do basically that same thing, except instead of bidders bidding on items, they're going to be able to bid on bundles. And instead of just one item having one price, we're going to allow different prices for different people. Okay? So each iteration as long as we're getting new bids, here's what we do. So at any given time, there'll be these PISs, okay, a price for each bundle in each bidder I. Now in general, these PISs might overlap, okay? It might be that at different parts in time, different bidders have bid for overlapping bundles, so we can't just regard all of these as being sold. So the seller has to somehow figure out which of these bundles it's going to actually tentatively accept at the moment. And so the seller just picks the allocation of items to bidders that maximizes the seller's revenue with respect to the current prices, the current PISs. So the seller computes the allocation S1 through Sn, maximizing its revenue. Okay, and all the PI of S's start at 0. Now, so if you're one of these bidders and you're not chosen, okay, so you wind up getting nothing, you're given an opportunity to bid again, bid on some bundle. So for each I, with nothing, the bidder I picks one of its favorite bundles at the current prices. And now remember, the current prices, actually, they're personalized, right? They're PI of S's. So bidder I says, well, you know, given the current price for me for any bundle, and given my values, which one gives me the highest utility? So pick S, I in argmax of its value for a bundle minus its current price at that bundle. And it's allowed to increment the price for that bundle by epsilon. Okay? And so notice bundles are chosen to maximize revenue, so by increasing the price on a bundle that has your name on it, you're more likely to get allocated in the next round by the seller. Okay? So initially, so if you think about this auction, initially sort of this is weird. All the prices are 0. So basically, if I'm a bidder, if all the prices are 0, I may as well just ask for everything. So in the first round, everybody asks for everything, and then the seller's just going to pick sort of one person arbitrarily. Everyone else will lose. And then they'll have to pick bundles that they want, and then slowly prices will be going up, and then eventually these will be sort of meaningful maximization problems. Okay? So basically, you'll have bidders focusing in on the bundles that give them the most utility at the current prices, and the seller's always just picking the highest revenue bundles. Okay? And you just let this go. Okay? All right, so, and again, so I would really just think of this as like that unit demand auction, except where we used to have the, it used to be that the fundamental things were items that people were bidding on. Now it's like the goods are bidder bundle pairs, I comma S. Right? So that's what gets incremented in a given round, something corresponding to a bidder I and a bundle. And just like the Crawford-Noer auction has certain properties at termination, so does this one. The proofs are pretty much the same. So properties. So if bidders bid sincerely, and that just means that they report a bona fide element of this maximizer. So if you have sincere bidding, then you terminate at the sort of suitable analog of a Walrasian equilibrium where you have bundle pricing. Okay? So that's called a competitive equilibrium in this context. And this first property is true with absolutely no assumptions at all about the valuations. Okay, so gross substitutes or not, doesn't matter. Okay? And the proof is exactly the same as the proof that the Crawford-Noer auction converges to a Walrasian equilibrium. It's like basically word for word the same. As far as what's the definition here just says the seller should be maximizing their revenue with the current prices. Obviously that's going to be true at termination. And then furthermore, from each bidder, they should be getting their favorite bundle at the current prices. And again, remember the prices are personalized and are bundle specific. And that's also sort of clear. I mean, that's how so a bidder is going to wind up at the end of the day getting some bundle that they bid on. And then what's happened since then, the prices of other bundles have gone up. Okay? So you only bid on a favorite bundle, and then if you get it, it only looks better as time proceeds. Okay? So it's the same proof as before. the first welfare theorem still holds. It's still the case that at a competitive equilibrium, it has to be a welfare maximizing allocation. Okay? Now, just to be clear, full disclosure, I mean, this could take forever to terminate. I mean, it's finite, but it could take a long, 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 long time. Okay? 2 reasons. First reason is there's just a lot of prices you have to maintain. Right? So for each bidder, there's n bidders. There's 2 to the m possible bundles S, and you're only incrementing 1 at a time. Okay? So it could take forever to get these high enough for it to be meaningful. Okay? In practice, of course, you'd increment lots of bundles at the same time. Okay? The second reason why there's no guarantee of quick convergence is that in general this could be an NP hard problem, okay? Asking the seller to find the revenue maximizing allocation. Okay? But whatever. I mean, we're doing this as sort of a proof of concept at the moment. So it's going to converge to a welfare maximizing allocation that doesn't contradict any NP hardness results we know for that problem, because this need not be efficient. So it converges to a welfare maximizing allocation, but we've now seen many cases where getting the allocation right with an ascending auction isn't necessarily the hard part, it's really getting the payments right. And again, we need that if we want to ex post set a compatible implementation. So what about the payments? And here we will say something only under the gross substitutes condition, okay? So if the VIs, so remember this thing, property 1 is true whatever the VIs. If the VIs satisfy the gross substitute condition, then in exactly the same way that in our unit demand auction, okay, so what's going on in general, so Crawford knower, just to remind you, not only did it converge to a Walrasian equilibrium, but it converged to the lowest Walrasian equilibrium. Again, under the unit demand assumption that coincided with the VCG payments. And so in the same way that unit demand was the magic condition that allowed the coincidence of the lowest Walrasian equilibrium and the VCG payments, for these bundle pricing auctions, not unit demand but gross substitutes is the magic condition that there's a notion of a lowest competitive equilibrium with gross substitutes valuations, and that again coincides with the VCG payments. Okay, and auctions like this will converge to the lowest competitive equilibrium, so under this assumption you do actually get the VCG payments. So a picture you might want to think about is, so you can imagine the world that we had the entire last 3 lectures on, which is the item pricing world, okay? Which is for each item, you maintain a price. If somebody gets a bundle of items, you just add up the prices in the bundle. Okay, that was the last 3 weeks. Item pricing, also called linear pricing. And so what do we see? We saw, well, if you just want equilibrium to exist at all, then you have to, so namely a Walrasian equilibrium, then you have to restrict attention to gross substitutes valuations. And if you want a coincidence between Walrasian equilibria and VCG payments, you have to restrict further to the unit demand case. Okay? So here we have existence of Walrasian equilibria. We proved this last week. And then here we actually have the lowest Walrasian equilibrium equals VCG. Okay, this was a pretty hard proof that we did in week 2. Okay? And so what I'm saying is that if you enlarge the space of auctions from just item pricing to these bundle prices, you get the same picture but sort of zoomed out. So with bundle pricing, now existence is no longer a problem. Existence of this competitive equilibrium. But if you want to converge to a VCG outcome, then you want gross substitutes. So lowest competitive equilibrium equals VCG. So for item pricing, gross substitutes is sort of the threshold of equilibrium existence. Okay, but it's actually too far to make it easy to compute the VCG outcome in an ascending way. With bundle pricing, gross substitutes is the frontier of attainability of conversion of the VCG outcome with simple ascending bundle price auctions. So again, as I've said, it's amazing how many different properties simultaneously gross substitutes is really kind of the limit of where you can get nice properties. So here we're seeing yet another one. So I should say, so you can ask about the converse. So we talked about last week how in some sense gross substitutes is the maximal class so that you get existence of all laws and equilibria. So you could ask the same question, is it the maximal class where you can get VCG payments within ascending auction? Almost. Okay, morally, basically, yes. Although, strictly speaking, a slightly weaker condition is the one that's necessary. So let me just say, and almost, only if. Okay? And, so as far as, how to approach people, right, so the theory starts breaking down at a certain point, but of course the problems don't go away, okay? We do have combinatorial auctions. We want to solve them with ascending implementations. Maybe, hopefully, gross substitute sort of holds, but it's not totally clear. So you might ask, what parts of this theory do people build on? And so we talked about this, last quarter. You can go read the notes if you want to review it. But just, a couple points. So first of all, one thing you can do is you can just stick with basically the Crawford nowhere auction in effect, okay? Or just assume there are substitutes, or I guess the Kelso Crawford auction. And even if there are gross substitutes valuations, we know it's not incentive compatible. We know there's incentives for demand reduction, but you could hope that it works good enough. And really for the 90s, that's what people were doing. Okay, so they knew it wasn't perfect. Empirically, you'd see evidence of demand reduction, but it wasn't a disaster. And like with billions of dollars, not a disaster was kind of a pretty good baseline. So people were okay with that and conservative in the 90s. And honestly, the last 10 to 15 years, there's been an enormous number of competing proposals and designs about how to incorporate this package or bundle bidding into combinatorial auctions. And it's been done in a limited way and in different ways in different countries. So there's two reasons, there's two main drivers for why people are trying to incorporate bundle or package bidding. The first is actually if you just don't have substitutes at all, if you have complements or synergies between different items. Then there's this exposure problem we've talked about on occasion. So you really want to help people vulnerable to the exposure problem. The second thing, although I think this is a less important point, is you might hope to reduce incentives for demand reduction also by allowing package bidding, say even if people had substitutes valuations. But I think the kind of arguments, the debates continue about the right way to do this, and there's no consensus, and I'm not seeing that there'll be a consensus soon. So this is very much the kind of stuff people who design auctions for a living struggle with. Okay? So that concludes everything I want to say about ascending implementations, and for now at least substitutes. Any questions about any of that? Okay. So I want to warn you, I'm pretty sure we're not going to see another ascending implementation for the rest of the course, because now we're going to look at slightly harder problems where essentially no ascending auctions with any kind of guarantees are known. That's basically an open question. For the rest of the scenarios we'll talk about, it's sort of open. Are there reasonable ascending auctions from them? Okay, so that's something to keep in mind. Okay, so that concludes part one of the class. Part two, we're going to go a little bit beyond these tractable special cases. And tractable means at the very least polynomial time welfare maximization. So now we're going to look at scenarios where we lose that property, where it's NP hard to do welfare maximization. As we'll see, as soon as that happens, there's a host of problems that arise for the mechanism designer. Okay? So let me take you one step, what would seem to be one small step beyond gross substitutes valuations. Okay? So sort of the next level of generality. So it's going to be submodular valuations. So this will be our scenario 6. So evaluation, so again, it's a set function. So it's submodular, and I think everyone's seen this definition last quarter at some point, at least on the homeworks, if nowhere else. If and only if. So here's the picture you want to have in mind. Okay, so here's the entire item set. Here's a bundle, small bundle. Here's a bigger bundle, T, and then there's an item which is outside of both. Okay. And we want to ask the question, what's the marginal value of requiring J, given that you already have some stuff? Okay? And submodular just says the marginal value of more stuff is less the more stuff you've already got. Okay? Diminishing returns. So if you already have T, and I give you J also, it's not as important to you, it's not worth as much, as if you merely have S, and I give you J. Okay? So this is for all S in T and for all J. The only interesting case is when J is outside of S and T, although it's true no matter what J is. Okay? All right, so the more you've got, the less you need more stuff. Submodular. So just real quick, so just to make, it's easiest to start with a non-example. We were sort of plagued last week by a valuation which at the time we observed was non-gross substitutes. Now we'll see it's also non-submodular. So the single-minded bidder, so let's say you're in all or nothing. Okay, you have value 1 for all the goods, even say there's only 2 goods, and you have value 0 if you don't get everything. Definitely not submodular. Is that clear? So say there's 2 goods. If I give you good A and you've got nothing, you're like, well, I still don't have everything, so it's still value 0. Okay, no marginal value. But if you already have 1 good, then the second good completes the set. Okay, and that gives you the bump up of 1 in value. Okay? All right. So that's exactly, that's a non-example of submodular. That's a violation. Now, intuitively, what you should be asking, how does this compare to the last one, to gross substitutes? And in particular, actually, are they different? They seem to be trying to say basically the same. The intuition is very similar behind the 2 definitions. Both are basically trying to say that, as goods are taken away from you, your value for what you've still got is only going up. Right? So that was sort of true in the substitutes case, right? You lose goods and you still retain the old ones. And this is also sort of saying, it's kind of like, well, if I had, think about J. If I had less stuff, then my marginal value for J would only be higher. And so they almost seem like the same. So let's spend a little time understanding how they relate to each other, because they're defined very differently. Okay, so first, the first claim is that submodular is at least as general as gross substitutes. Okay, so if you satisfy the GS condition, then you must be a submodular valuation. For some reason, this seems to have only been proven by Gould and Stigeti in '99. But that's where it's from. Okay, so this takes a proof just because the definition of the two concepts are so different, right? So gross substitutes, it's not even directly a definition on the valuation. It's more the discussion of the demanded sets as prices vary. Okay, so it's just defined in a totally different way than a condition directly on the valuation, the values of various sets. So, how are we going to do this? So suppose we have a gross substitutes valuation. Okay? And fix an S and a T and a J. Okay, we want to prove it's submodular. So we want to prove that this holds for V. All right, so somehow in our proof, we have to have some of these sets appear, right, in our proof somehow. Right, and pretty much the only thing gross substitutes refers to is sort of your favorite bundles at given prices, demanded sets. So let's start, so to invoke the gross substitutes hypothesis, we need to start feeding it price vectors, right? And we want sets that look like this. So let's start with T plus J. So let me see, how could I get T plus J out of the gross substitutes condition? How could I get that to be a favorite set? Well, actually, I guess there's a sort of an easy way to do that, right? So let's just make the prices outside of T and J plus infinity. And let's make the prices inside 0. For starters, at least. Okay? So step 1, let P equal 0 for T union J, infinity, otherwise. And remember, valuations are always monotone. Okay, it's always free disposal. Well, so now it's kind of a no-brainer, right? So definitely, T plus J is a favorite bundle. Right? You don't have to pay anything for it, and any other good would just, give you negative utility. It need not be the unique favorite bundle. Right? Maybe there's some good in T that you could care less about, but it's a favorite bundle. Okay. So T plus J, so remember this is the notation, capital D. So there's only one valuation, so there's no subscript I. So this just means it's a utility maximizing bundle for you at the prices P. Okay, so we want some comparison of T plus J and T. So somehow we want to manipulate these price vectors so we get something about the set T, all right? So how are we going to do that? We're going to do that. We're going to say, okay, well, let's slowly make the item J less and less attractive, okay? So imagine gradually raising the price from 0 on item J. All the other prices stay the same. So think about, so you're a bidder with this valuation. Think about how your utility for the different bundles are changing as the price goes up on J. Okay? So if it's a bundle that doesn't include, okay, so bundles that are, so the whole universe is T union J at this point, right? Everything else is obviously irrelevant. So for a bundle that does not include J, so for any subsets of T, you don't care, right? Because J is not a part of it, that's the only price that's changing, so it doesn't matter. So those all, the utility stays exactly the same. For any bundle that does include J, the net utility is going down at unit rate, okay? Because the price on J is going up, so utility is going down, right? So there's going to be some point at which you like some bundle entirely inside T, some bundle that doesn't include J, at least as much as the bundle T plus J, okay? Because T plus J is getting worse, so is everything else that includes J, and everything inside T is staying the same. So at some point there's this first point at which there's a tie between a bundle inside T and a bundle that includes J. So epsilon we'll call the price at which that tie first happens, okay? So step 2, epsilon is the smallest price, so that a bundle that excludes J, that is a subset of T, is also in the demand set. Okay, so I'm going to call P epsilon this price vector, which is epsilon on J, 0 on T, plus infinity elsewhere. So let me update the picture. That's an epsilon. Okay? So T plus J is still a favored bundle, right? We stopped epsilon just before it would go away, okay? And now there's some other thing tied for it that's just inside T, okay? All right, so the claim is, in fact, so there's some subset of T inside this favored bundle. I claim actually T, at this point, T itself has to be a favored bundle. And now I'm actually going to use the gross substitutes condition. I haven't yet, okay? So the claim is by GS, T is a member of this demanded set. Okay? So why? Well, maybe think about it by contradiction. Okay? So we chose epsilon so that some subset of T is a favored bundle at this point. So if T isn't one of them, it means only strict subsets of T are utility maximizing bundles at this point. Okay? Only strict subsets of T. All right? So now jack up the price on J a little bit further, okay? Now, okay, so what's happening? Again, so as you jack up the price on J, everything inside T is the same as ever. Anything that includes J is getting worse, okay? So epsilon is the point at which any bundle that includes good J is about to disappear from the demanded set. Okay, they're just about to go away, okay? So they all go away, and if you don't have T, you only have strict subsets of T, okay? But this violates GS. Okay, we had a price vector where a demanded set was T plus J. The only price we increased was J. Gross substitute says there has to be a new demanded set that is a superset of T. Okay? Otherwise, we increased only on J, and all of a sudden we want to relinquish one of the items in T. That's a violation of GS. Okay? So, that's good. We have T plus J showing up in the proof. We have T showing up in the proof. That's what we want a relationship between. So, in fact, right now we know exactly what is the difference between this bidder's valuation, this bidder's value for T and its value for T plus J, which is what? Epsilon. Good. So because of this, right, so remember, also T plus J is in this demanded set. Right, we chose epsilon, so that was true. So that means the utility the bidder gets from these two bundles is a tie. Okay? So what's the difference between the prices? Well, one has the good J, one doesn't. The good J has price epsilon. Okay? So the values have to differ by exactly the same amount. Okay? Agreed? All right. So that's good. We've got 2 of the 4 in the proof. So how do we get the rest? Well, let's make everything in T but not S irrelevant. Okay? So let's actually let's now raise the price again. So everything in T minus S is infinity, and everything in S stays 0. Okay? And J stays at epsilon. Right? Because gross substitutes, we can sort of only control things if prices only go up. Okay, so we don't want a price to go down. Okay? So step 3, raise prices on T minus S to plus infinity, call the new price vector Q epsilon. Again, remember J's price remains epsilon. Okay, so what's obvious is that the only things with finite prices are in S and J, so any favored bundle at Q epsilon has to be a subset of S plus J. So only subsets of S plus J are in D of Q epsilon. And actually gross substitutes tells us something stronger than that, which is what? You see? Well, that's close. Sort of kind of a dual statement. You may also get some strict subsets, but you can't only have strict subsets. Exactly. So you got to have S plus J in there, right? Why? Well, what does gross substitutes say? Okay, so you have this price vector P epsilon. T plus J is a demanded good. I've only increased prices on T minus S, and the condition says you don't want to relinquish anything that hasn't been increased. You don't want to relinquish any of S plus J. Okay? So by GS, S plus J is a member of the favored bundles at this price vector.
So is S.
I don't know. Oh, yeah. Yes, applying it to T. You're right. We're not going to use that property, but you're absolutely right. Oh, I see. That's interesting, actually. Huh. Okay. Right, so I'm going to write down the inequality we need, but I guess equality actually holds. So in particular, just from this property, the bidder likes S plus J at least as much as it likes S, okay, which is actually all we need. So util for S plus J, and again, this is at the prices Q epsilon, is at least the utility for S, just because S plus J is a favorite. And again, the only difference between these two, as far as the prices, is that the price overall here is exactly epsilon more. Okay? So its value for S plus J must be at least epsilon more than its value for S for this inequality to hold. Okay? So that completes the proof. Okay? So at least we're trying to get some understanding of the relationship between, in fact, even if you didn't care about submodular valuations per se, this is something you'd want to know about gross substitutes valuations. This is just a little bit, I think, easier to get your head around as opposed to the definition of gross substitutes. Okay, so they're always submodular. Good to know. All right, and you may, it would be totally reasonable to wonder at this point if actually they're the same definition. So I'll leave it as an exercise to prove that if there's only 2 items, so in that special case, then in fact the 2 definitions do coincide. Okay?
Doesn't
we said S, this is actually holding with equality. So if you get restricted equality, you will get a full value gross substitute.
Something's fishy though. So, I mean, it's not. Let me think for a sec. I mean, it's not, I mean, gross substitutes doesn't imply that it's an additive function. So, I have to think about it. I have to think about it. It does seem like this proves something stronger, but I mean, it's not, but I mean, yeah. I mean, gross substitutes include things that are not additive, as we know. So, I have to figure out exactly what this statement is. Okay.
So when you remove the elements in T minus S, right?
Yeah?
So if you loosen the set which is tied with the current set in T,
Yeah?
so you have to like increase the epsilon further to actually get a tie.
Yeah, that's what but so what, like where in the proof?
So I think equality wouldn't hold in this case.
Right, so we argue, I mean, the thing that, so here's the reason why it kind of seems, let's see, so, I mean, T is one demanded set at this point, right? And then if I increase everything in T minus S, I see.
So
I see.
It's common to.
Yes, the point is S plus J would still count. Yeah, so you need not have S. Okay, good, yeah. All right, so gross substitutes just says basically, so you might want to acquire new things. You just don't want to drop old stuff, right? So maybe once I sort of obliterate T minus S, you used to be like, oh, I really want T. Okay, and now I obliterate T minus S. You're like, okay, well, I don't want those. I still want S, so I'm satisfying the gross substitutes condition, but now I want J also. So it could be that S plus J is the unique. So once you pass to Q epsilon, it could be S plus J is unique. Okay, good. Yep, thank you. Okay, excellent. So with m equal 2, in fact, gross substitutes is equivalent to submodular, which is equivalent to just being subadditive, meaning your value for both goods is at most the sum of your values for the singletons. Okay, so that's easy to prove. So they coincide for 2 items. They do not coincide for 3 or more items. Okay? So you can be submodular without satisfying the gross substitutes condition. Let me give you an example. Actually, a student basically gave this counterexample for the exercise set, so I'm just going to reuse it in lecture. So let me show you an example of what's called a budgeted additive valuation. So say there's 3 items, and you have values for the items, 1, 2, and 3. And your valuation's additive, except there's some limit on how much utility you can have, on how much value you can have. Okay, so I'm going to cap it at 3. So let's say that your value for a set S is going to be the minimum of 3 and the sum of your singleton values. Okay? Make sense? Right, so you can't get 6. Right, so if you get all 3 items, it's still just 3. Okay? So this is submodular. I'll leave you to check this in the privacy of your own home. It's not hard. I mean, basically just the contribution of an item, the marginal value is always the same, except when it exceeds the cap, in which case, you only get up to the cap. And the more other items you have, the closer you are to the cap, so the less the marginal value. Okay, so that's the proof. And to see that it's not gross substitutes, I need to show you the price vectors. So so how about the price vector on ABC, 1/2, 1/2, 2. So if you have this valuation and those are the prices on goods ABC, which do you want? What maximizes your utility?
All 3.
Don't forget about the cap, right? So if the prices are strictly positive, you never want all three, right? Because, right, so the highest this can be is 3. So remember, the prices you pay are not capped. Like, you just pay the money no matter what. And then when you're computing the value part of your utility function, there's no reason, once you have the third good, there's no reason to have more. Once you have the first two, there's no reason to add the third. A and B, exactly. Okay, so A and B will get you a utility of 2, and that's the best you can do. And then what if we go instead, what if we raise the price on good B? Then what do we want? Yeah, then we just want C. Okay? For a utility of 1. And again, because the value is capped, again, you might think we want to add A because the value is 1 and the cost is 1/2. But again, remember, once we have good C, the marginal value of A is 0. So at a positive price, you don't want to add it. Okay? So that shows explicitly that so gross substitutes is a strictly stronger condition than submodular. Okay? So in other words, if you sort of remember our picture, so now things are looking like this. And then we have this sort of interesting, subclasses of gross substitutes, right? So we have unit demand, we have sort of identical, we have additive, and so on. But this is how the hierarchy is getting built up. Okay? All right, so any questions about that? So definition of submodular, strictly more general than gross substitutes. Okay, so it's more ambitious to do anything with submodular valuations. Okay? And life was already getting a little complicated with gross substitutes, so got to be ready. All right, so now I want to talk about welfare maximization. Okay, so the same problem that we were obsessed with last week in the second lecture. We worked hard, used the ellipsoid algorithm. We did it with gross substitutes. What happens with submodular? Okay. Well, we can't do as well. Okay, we can't get polynomial time welfare maximization exactly. Okay, so an easy fact, another optional exercise. If you have submodular valuations, can't max welfare, let's just say NP hard to maximize welfare. And so one easy reduction is from partition. Certainly there are stronger negative results known, but if you just want to establish NP hardness, that's an easy way to do it. Now we talked last week about, with these sort of combinatorial valuations, when you talk about polynomial or NP hard, you have to specify what's the input size. So I should be a little bit more precise here, but I mean, this hardness result is so easy, like it never comes up, basically. So this is already true if you just have 2 bidders, and if they just have these budgeted additive valuations, okay? And so these you can just write down explicitly as input. Remember what we're worried about. We're worried that the input size is 2 to the m, and trivializing the problem. But with these special valuations, obviously the input size is just going to be n times m, I guess. Okay, polynomial in n and m. So even for that special case where you can really talk about polynomial and input size in the normal way, it's already NP hard. Okay? So this, if you like, if you believe in p not equal to np, that says we didn't need this example, right? We'd know just from this fact that actually there's a difference, that submodular is strictly more general, okay? Because there's things we can do for gross substitutes that we can't do for submodular. Okay, so time to take a step back, zoom out, and recall the forest. Sort of recall what we've been after in the course so far. So there are these 3 things we wanted, okay, which sometimes I call awesome auctions, right? And so we said, well, okay, we want the best case scenario along every possible axis. Okay, the first axis being the incentive guarantees. We want them to be as strong as possible. So for direct revelation mechanisms, which is now what we're talking about, it would be dominant strategy and incentive compatibility. We want the best imaginable performance guarantee, assuming we care about welfare maximization. So that was the second one, and then we wanted tractability. So at the very least, polynomial time, ideally somehow simple and natural on top of that. Okay? And for the tractable special cases, we were getting all this stuff. So, okay, so now what are we hoping we might be able to get? Okay, so from this NP hardness result, we conclude that, well, forget about 1, right? 2 and 3 already we cannot attain at the same time, assuming P is not equal to NP, right? So that's what we just learned. Okay, even for submodular valuations, 2 and 3 are in conflict. So, right, so relaxing 1 won't help us with that problem, right? So that's not a way out. So what we're going to look at is going to look at relaxing 2. Okay? So we want to approximately maximize welfare. So in some sense, these will be approximately awesome auctions. And this is going to be the subject of this week and next week. Okay, so that's part 2 of the course. Okay, so we're going to still be hardliners about how strong an incentive compatibility guarantee we want. We're going to stick with DSIC. And then subject to that, we're going to ask, to what extent can we get 2 and 3 simultaneously? Okay. So now I want to warn you, so this part of the class, this week and next week, will probably have the most complicated mechanisms in the class. Okay, the good news is there'll be DSIC, so like if you actually had to play in one, it wouldn't be hard. You have a dominant strategy, which is just direct revelations. That's not a big deal. But I mean, these will be kind of almost all just purely theoretical constructs, proofs of principle of tractability, okay? So somehow insisting on DSIC really, first of all, there's impossibility results. There's lots of stuff you just fundamentally cannot do. Okay, and I probably won't prove those impossibility results, but I'll survey them. And the stuff that you can do, which is what I'll focus on, you have to work really quite hard to do it. It'll probably be some of the more intense algorithms some of you have ever seen, actually. Okay? So just brace yourself for that, especially next week. So then, after a couple weeks of realizing how much we have to suffer if we insist on dominant strategy and compatibility, we'll take a step back and we'll relax this. Okay? And so in part 3 of the course, we'll look at relaxing this to undominated strategies. We'll talk about that a little bit. And we'll talk about Bayes-Nash implementations. Okay? So then the good news is we'll be getting we'll be doing much better with respect to the positive results. Okay? We'll be getting better approximations for a wider class of problems. The mechanisms will still, though, mostly feel like theoretical constructs. Okay? They'll still be pretty complicated. So in part 4, what we're going to do is we're actually going to take the simplicity constraint as the hard constraint. Okay? And so we're going to say, let's insist on simple auctions, which, though may not be very easy to play as a bidder, okay, so the equilibria set may be complicated, but at least the mechanisms are simple. And we're going to ask, how well can we do? Okay? So what kind of approximations do we get at equilibrium? Okay? And then time permitting, at the end of the course, we'll switch to revenue maximization, okay, which sort of has a different flavor. Okay, so that's sort of the high-level comments about where we stand. Any comments or questions about that? All right. Any other warnings that I owe you? Okay, good. All right, so that's where we are. Okay, when can we get 1 through 3? For example, for submodular valuations. Okay. Well, let's begin with an easier question, which is when can we at least get 2 and 3? Okay, because at the very least, you got to figure people have been thinking about that for like 30 or 40 years, and they have. That's just approximation algorithms. Okay, and the literature on approximation algorithms is very, very rich. So that'll draw some lines in the sand of what we might possibly hope to accomplish. All right. So prereq. How about just 2 and 3? Okay. Now, of course, ultimately we want to extend these approximation algorithms into incentive-compatible mechanisms, but let's just do it one step at a time. All right, and so the good news is actually, so the news is quite good for submodular valuations if we just want polynomial time good approximation. It's NP hard, but it turns out we can get quite good constant factor approximations. Okay? Actually, something I've already showed you already is a good approximation algorithm for submodular welfare maximization. Okay, so that's what I want to conclude this first lecture of the day with. So theorem. So again, a positive answer to this question for scenario 6, submodular valuations. And so this is a recent result just from about a year ago. Here's what we're going to do. Okay? We're just going to run the Kelso Crawford auction. Okay, and I'll review the key points of it in a second, but that was the one that worked for gross substitutes. So Crawford Knower was for unit demand, where bidders just bid on one good. And then we had gross substitutes where they could bid on a bundle. Okay, but otherwise it was the same. And so we were talking about all of that auction seems totally engineered for gross substitutes, right? Because basically that's the condition you need for people to not want to relinquish items and terminate over laws in equilibrium, blah, 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 blah. So we're going to go ahead and run that auction, okay? Even though the bidders will have submodular non-gross substitutes valuations. We're going to run it till completion. And we're actually going to argue that at completion it's almost optimal. It's not optimal, because there may not be laws in equilibria, but it's within a factor of 2. Okay? So if all bidders have submodular valuations and bid sincerely, remember we're not, the point here is just to have an algorithm. I'm not talking about incentives, okay? The point is just an algorithm. Okay, so I'm just going to simulate sincere bidding for these bidders to compute an allocation. So if everybody has submodular valuations and bids sincerely in the Kelso Crawford auction, then I claim it terminates with an allocation with welfare at least half of optimal. Okay? So with gross substitutes, you get 100% of optimal, because you'll converge to laws in equilibrium. Here there are no laws in equilibria, and we know it's NP hard to compute an optimal anyways, but it's going to terminate with something within 50%. Now 50% maybe isn't like the best approximation factor you've ever heard, but you know, frankly, most NP hard problems you can't get a constant factor at all in polynomial time, including for lots of welfare maximization problems. So this isn't that bad. If you really care about submodular valuations, there are other algorithms which do better than 50%. You can get, I think 63% or something like that. And that's one of the projects if you're interested. Okay, so there are somewhat better algorithms. But honestly, again, as these things go, we should be happy with this. Okay, for worst case guarantees, they don't usually get too much better than this. Okay? All right. I should also say, historically, people usually will know and teach a different older 2 approximation algorithm by Lehman, and Nissan. That's a simple greedy algorithm, and that's outlined also in the exercises. Okay, but I wanted to do this one because we basically already know the algorithm, and it's kind of cool that it just works. All right. So let me mention a couple salient points of the Kelso Crawford auction, and then think about what you don't remember and ask me, and I'll elaborate. Okay? But so here's sort of the key points. Right, so initially, all the prices are 0, and then every time somebody bids on an item, the price gets bumped up by epsilon. One really important property, I made a big deal of this at the time, is that there's no bid withdrawals. Okay? So if you're the tentative winner of an item at a given price, whatever happens with the other items, it doesn't matter. Okay, I'm not going to let you relinquish this item. Okay, and that's by definition of the auction. Okay, that's what motivated the gross substitutes condition in the first place. Okay, we wanted to argue that that's not a bad thing, that people can't relinquish items because they don't want to anyways. So that's an important property. With submodular valuations, people might actually want to withdraw their bid, okay, because they're not gross substitutes, but we're not going to let them. Okay. So in particular, if you think about it, remember an important property here was that condition in the laws in equilibria that unsold goods have price 0. Okay? How could it be that you didn't get sold? It has to have meant that nobody ever bid on you. Because again, if someone ever bids on you, then the only thing that ever happens is you exchange hands between bidders. Okay? You never become unassigned. So the only way you are unsold is to have price 0. And we're going to use that in the proof of this theorem. Okay, so what else? And then right, so then what do bidders actually do? Well, Well, so if a given iteration, some bidder has some current set of items SI, we ask if it wants any new ones. And if it does, we say, tell me your favorite set. Okay, the items TI you want to add to the ones you've already got. Okay? And then when it says, I want these goods TI, you take them away from the current owners, you reassign them to I, and all those prices get bumped up by epsilon. And that's the Kelso Crawford auction. Okay? So I bids for best set TI of new items given, of course, the current set of prices plus the items SI it already has. Okay, so it's doing some argmax over the item set U minus the items SI that it already has. Okay, and among all those subsets, it picks the best one, utility maximizing one. Okay? So does anyone want any more review of Kelso Crawford? Is this enough? Does this make sense? Okay. All right. So we're going to prove that this terminates with a true approximation for submodular valuations. Okay. So proof. Okay, right. What am I proving? Let me tell you what I'm proving first. So here's an important lemma. And it's going to sound weak, but actually this is really where the submodularity condition is important. So at termination, and again, we're always assuming sincere bidding, all bidder utilities are non-negative. Okay? So this should feel kind of weak. So for gross substitutes, we were saying it was a Lavoisian equilibrium. So we're actually saying that every bidder has its best bundle, utility maximizing bundle. Okay? So all I'm saying is now, there might be bundles that wants a lot more than the one it's got, but at least, it's not paying more than its value for what it has at termination. And let me remind you, actually, when I kind of showed you that disastrous things can happen in the Kelso Crawford auction, this was violated. So what we did is we ran the Kelso Crawford auction with a single-minded bidder, one of these all or nothing bidders. And if it bid sincerely, it actually wound up with utility -1. Okay, we saw that last week. All right, so there's definitely going to be evaluations where this doesn't happen. Okay, so proof. And this is really where submodularity of the valuations gets used. Yeah. All right, so the invariant will be the following. At all times in this algorithm for all bidders, consider a bidder I currently with items SI for all subsets of its items. Bidder I's value for that subset of items is at least the price it's paying for those items. Okay? So we're going to prove a stronger statement, okay, for the induction, right? So what I want to be true, I just want to be true that at the end of the algorithm, the bundle that a bidder actually winds up with, it's not paying too much for. Now remember that what's tricky about this auction is, you bid for some bundle and it looks really good at the time, but then people take these items away from you, okay? So the problem is sort of at the end of the auction, you might wind up with this bundle that you didn't bid on. You bid on something much bigger and all these pieces were sort of taken away from you by other people. So that's why I want this invariant that applies to every single subset of the items I currently have, because any of those might be my allocation at the end of the auction. Okay? So is this clear? Right, so SI is what I has right now. There are some prices. I want to say whatever subset it winds up with, it's going to be fine. It's going to have non-negative utility. Right? That's what I want to prove. Okay? So base case, everyone's got nothing at the beginning, so this is fine. Right? Also, for the inductive step, almost all the work takes care of itself. So consider an iteration. So suppose I has SI and bids for new items TI. Okay? Now, most of the invariant is just going to be fine, okay, because I've made it so strong, right? So which bidder, who is the only bidder whose invariant might get screwed up? Right, so bidder I is taking items away from everybody else in this iteration. Okay, so it says TI, I want those, and it takes them from people. Okay, so suppose you're some other bidder K different than I. Okay, so what happens, right? You had this bundle of goods, you were perfectly happy with whatever subset you were going to get, and now some were taken away, but the prices on what you still have are unchanged, so you're still going to be happy with whatever subset you might get. Okay, no problem. So, variance still holds for K not equal to I. Okay, so we just had to show that I didn't screw up the invariant by acquiring these new goods T sub I. Okay, that's the key point of the proof. All right, so let's actually do that. All right, so for I, let's proceed by contradiction. Contradiction. Suppose there is some set, let's call it A, in its new bundle of goods, SI union TI, so that the prices are strictly bigger than its value for it. Okay? So here are the old items, here are the new items. In general, this set A, as far as we know, might span both. Okay? I'm going to call the subset of the old items in A X, and I'll call the subset of the new items in A Y. Okay? So X is just A projected onto SI, Y is A projected onto TI. Okay? All right. So, does the inductive hypothesis tell us anything here? So Y is the new stuff, right?
A can't be an SI.
Agreed. Definitely agree. A can't be an SI. And in fact, more generally, the part of A that projects into SI, namely X, satisfies this condition. Okay? Because everything in SI satisfies this condition. Okay? So by IH, we have VI of X, at least this. And yet, by assumption, if we add in all the elements to Y, i.e., X union, remember X union Y equals A, and A is our bad set, this inequality flips. Okay? So this is where we stand. All right? So now what I want you to imagine we start with the set X, okay? And we sort of track, both the left-hand side, the value, and the right-hand side, what you're paying. Track both of those quantities as we add the elements of Y, the items of Y in one at a time. Okay? So both are getting bigger, but possibly at different rates. Okay? So in particular, we start with the left-hand side being bigger. All right, so say there's like, L items in here. All right? We're going to add them one at a time. There'll be, at some point, right, all of a sudden, this flips from there to there. Okay, there's some item at which all of a sudden, this holds. Okay? So let's just rename so that Y has the items 1 through L. Consider the first time where it flips. So why would it flip? Right? So when it flips, okay, so if this holds and suddenly it flips, well, I guess this didn't go up by as much as this. So I guess the marginal value of adding that item over here was less than the price that's being paid for it. That is, okay, so again, we look at, this is just the marginal value of adding J. This must have been less than PJ. Agreed? That's the only way the thing flips. Okay. Well, now this is starting to look kind of in the wheelhouse of submodularity, right? We're talking about sort of marginal values of adding one extra item. What does submodularity say? It says adding an item to a bigger set is even less useful than adding it to a smaller set. Okay? So what we're having here is that adding J to this set is not very useful, and that's going to be even more true if we think about adding it to everything other than it in A. So let me say that again. So by submodularity, let's think about, I don't even want to do that. Wait, hold on a second. V minus S union. Yeah, okay. So let's actually expand all the way out to SI union TI. And let me remind you the definition of TI. We asked this bidder, we said, look, you've already got SI. Given that, what else do you want? And give me your best answer. Okay, what would maximize utility among anything else you might pick? And they said TI. Okay? But let's think about it. Like why not say TI minus J instead? Right? So like even if you only had this very small subset of goods, J doesn't really do you much good. Right? It's sort of less than the price you're paying for it. So why on earth did you want to add that to this much bigger set, SI union TI minus J? So by submodularity, the marginal value of adding J, remember J is in T, don't forget, J. Okay, so the marginal value of adding J to everything you've got, this is even smaller than this, so this is also less than PJ. But then that means TI wasn't your utility maximizing subset of items to add. Okay, TI minus J would have been an even better set to add. Okay, because if you deleted J from TI, your marginal value wouldn't increase by very much, but the price you pay decreases by even more. Okay. So then TI minus J, better to add than TI, so there's our contradiction. Okay? So that was the key lemma. That's somehow like the hardest work in this factor 2 proof. Okay, right there. So that's great. Okay, so people don't necessarily have their favorite bundle, but at least they have non-negative utility at the end of the day. And as I said, we know that's not true without submodularity. All right. So here's a corollary. And this is sort of the consequence of this lemma that will be directly useful when we prove the approximation bound. And the corollary says, look at the prices at the end of this auction. So suppose when we run the Kelso Crawford auction, the final prices are P, and the final allocation is S1 through N. Then the claim is the sum of the prices at termination are bounded above by the welfare of the allocation. Okay. So then sum over PJ, J and U is at most the welfare achieved. Okay? So again, it won't be clear why this is an interesting statement until we prove the theorem. But this is what we'll use directly. So proof. So let's also recall, and this is sort of a key property of the Kelso Crawford auction, the only way that a good goes unsold is if it has price 0. Okay, so how am I going to use that now? Well, the sum of the prices overall equals the sum of the prices of the goods that were sold, because the remainder is 0. One way I can count up the sum of the prices of the goods that were sold is by just iterating over all the bidders and looking at what goods they got. Okay. That's just iterating over the sold goods. And by the key lemma, bidder by bidder, this is bounded above by the welfare of that bidder at termination. Okay? That's the corollary. We can lower bound the welfare achieved by the final prices of all the items. So why does Kelso Crawford terminate with a 2 approximation? So this may give you flashbacks to the price of anarchy segment of last quarter's course. So let P and S1 through Sn be as above. So final prices, final allocation. And we want to compare ourselves to the optimal allocation. We want to say we're almost as good at termination. So let S1 star through Sn star be the optimal allocation. Okay, welfare maximizing. Now, at termination of the Kelso Crawford auction, nobody wants to add any new stuff. Okay? So in particular, if I'm a bidder, I've got some items, and maybe sort of there are these items I'm supposed to have in the optimal allocation and I don't have them. But I decided not to bid on them. Okay, why not? Well, I guess it would have made my utility worse. Okay. So at termination, for all I, if I did a cost-benefit analysis of grabbing the items that I have in the optimal allocation but that I don't have now, it would come up negative or non-positive. Okay, so if I do the thought experiment, I say, well, you know, what would be my extra value getting those goods that I don't have in the optimal allocation? Well, I guess that would be at most what I'd pay. So strictly speaking, because of the epsilon stuff, there's a, you know, up to an epsilon error per good, but whatever. Among friends, forget the epsilons. And let's just go ahead and be sloppy and upper bound that by the sum of the prices of everything I'm supposed to get in the optimal solution. Okay? So that's just the termination condition. Let me be even sloppier, actually. Let me make this even more true by making the left-hand side even smaller. So by monotonicity, I can lower bound this by just the welfare that player I gets in the optimal allocation. Is that too bad? So sorry, let me put that on top. So basically I had this one inequality, which is just immediate from the termination condition of Kelso Crawford. I declined to try to get these bids, these items from S star minus S. That's where this comes from. Now I'm doing two sloppy inequalities. Here's the first one. I'm just throwing in more prices, which can only be positive. And then over here, so that just makes this bigger. And then over here, I'm lower bounding this because VI is monotone, remember, free disposal. I'm making this only more true if I replace this by VI of S star I. So summing over all bidders. So again, remember this is true for each bidder. No bidder wanted to grab any more items at the end of the auction. So we have sum of the optimal allocation welfare terms minus the sum of the algorithms welfare terms. At most, sum over I, sum over the goods that I gets in the optimal allocation. Which, by the corollary, let's remember our corollary says that the final prices are bounded above by the welfare of the final allocation. So that's what I'm using here. So this is just a subset of the final prices. So all of the prices are only bigger. The corollary says I can bound this by the welfare. And now I just move this over, divide by 2. And we get that the welfare at termination is at least 1/2 of the optimal welfare. Okay? So again, so to sort of jog your memory of how a lot of the price of anarchy analyses worked, which is basically the template we're copying here, you halt with some kind of equilibrium. I mean, there's no formal equilibrium concept here, but there's this termination condition which has the same flavor. Nobody wants new items, so you can think of that as like an equilibrium condition. That generates an inequality for each bidder, relating its utility, well, its welfare at the algorithm to that in an optimal allocation. We get one of those inequalities for each of the bidders, and then we combine them and rearrange. And then the key lemma was just saying that, you know, when we look at all of those quote-unquote equilibrium conditions, we have this error term, which is the sum of the prices. Okay, so if that error term was too big, we'd be hosed, but we use submodularity to argue that it's not, that actually we can relate that back to the welfare of the final allocation, which gives us the factor 2. Okay? All right, so I think it's time for a break, so I'll see you in about 10 minutes.